Hello everyone, my name is Dmitry Vostokov and I introduce systemic software diagnostics today. This is a version 1 of the webinar in order not to overwhelm you with concepts. So I decided to keep this presentation as simple as possible and as short as possible. I suppose you all enjoy diagnosing software problems, but feel a bit restricted by the traditional software troubleshooting and debugging techniques. If you are also bored to death by software trace analysis in a large software factory, you may find a material presented here refreshing. But first we need to explain some phrases we use, such as software diagnostics and also system theory and thinking, that is sometimes called general systems theory. Software diagnostics can be defined as a recognition of patterns of abnormal or irregular software structure and behavior in various software artifacts such as memory snapshots and software traces and logs. Actually, do you hear me well?
The broadcast is now starting. All attendees are in listen-only mode.
Hello all again. Do you hear me well? So I repeat the first slides because there was slight problem. So hello everyone, my name is Dmitry Vostokov and I introduce systemic software diagnostics today. This is a version 1 of the webinar in order not to overwhelm you with concepts. So I decided to keep this presentation as simple as possible and as short as possible. I suppose you all enjoy diagnosing software problems, but feel a bit restricted by the traditional software troubleshooting and debugging techniques. If you are also bored to death by software trace analysis in a large software factory, you may find the material presented here refreshing. But first we need to explain some phrases we use, such as software diagnostics and also systems theory, that is sometimes called general systems theory and thinking. Software diagnostics can be defined as a recognition of patterns of abnormal or irregular software structure and behavior in various software artifacts such as memory snapshots and software traces and logs. It needs to be distinct from software problem solving because there can be unnoticed hidden problems that first need to be diagnosed. This is especially true for system monitoring and diagnosing emerging problems. At the same time, software diagnostics is a part of software problem solving, such as software troubleshooting and debugging, that is always done incrementally and iteratively. Now we try to give a definition to system theory with a focus on software systems. Please find that we stress on generality of systems theories not a theory of general systems here, as there is no such thing as a general systems. Thanks to Facets of System Science book that pointed to that distinction, I put a reference to such a wonderful book at the end of this presentation. A diagram here makes the notion of systems clear. An example such as a building is too trivial to discuss here. For a non-trivial example, we can find a narrative fiction system in a real or imaginary world as clearly embedded and delineated with certain narrative parts serving various functions. At the same time, consider a bounded region of memory with components inside associated with certain functions and having interfaces. So we are concerned with general similarities in organized systems and not with banalities such as statements that a software system consists of subsystems and so on. Okay, it seems to be a restored sound. So I suppose you all clear me well. All hear me well. Why do we need general systems approach? Because of organized complexity of software as human artifacts, we would like to look at other organized complex artifacts of human activity and find common threads to improve our diagnostics and ultimately problem-solving ability. This webinar is a loose association of ideas from general systems theory with proposed and already implemented applications to diagnostics, troubleshooting, and debugging. Due to time constraints, I didn't include all that I planned initially, with many slides omitted, so I also plan to do an update webinar early next year. Software diagnostics can be defined as a search for patterns in software execution artifacts, so it is essentially pattern-driven. This aspect was covered in the previous webinar on pattern-driven software diagnostics, and a link to that you can find at the end of this presentation on a resources slide. Here we cover systemic approach, using other systems because of similarities between them and software systems. The relationship between system and environment is one of the critical relations in systems. So for this obvious statement about this relationship of a software program as a system and its environment, I would like to highlight two patterns, such as not my version, that also exists in a hardware variant, and changed environment pattern that we discerned some time ago. You get all these links when I upload PDF version of this presentation. The recent proliferation of value-added software and malware is covered in structural and behavioral patterns related to the so-called hooksware. Now we come to the use of common aspects of human systems in software diagnostics that is currently considered as a deterministic, mechanistic, machine-like system in the mainstream of software engineering and computer science. In the past, such anthropomorphic attempts had failed. For example, the so-called organismic approaches at the end of the 19th and the beginning of the 20th century. This was mainly to the unknown functioning of organisms and self-organized societies. As software systems are created by humans, we can use methods of certain disciplines to study software artifacts. Now we know much more in humanities and social sciences compared with a century ago. And typical example is using, for example, literary narratology for structuring software traces and logs, which are viewed as stories of computation. The link to another webinar on software narratology is provided on the resources slide. So far, we have seen examples of the so-called isomorphic systems, systems which have similar properties and methods. This is a typical example of general systems approach. And as a consequence of isomorphic systems, we also have isomorphic patterns, for example, patterns of narrative in fiction and in software artifacts. Another example is similarity of memory dump analysis patterns in crash dumps from Windows and core dumps from Unix. Additionally, we can also consider similarities between different software artifact types. For example, memory dumps can contain traces and logs, can contain mini-dumps, another type of isomorphism. And still another example is similarity between different types of diagnostics activities, such as between software trace analysis and network trace analysis, where packet headers represent software trace messages. Here I provided also a link to a case study with pictures, so you can later look when you download PDF file of this presentation. At the high level of abstraction, we have the so-called isomorphic disciplines. You all are familiar with the notion of a metaphor. So the extension of a metaphor can be thought as a function which projects vocabulary, ideas, theories and methods from one discipline to another and enriches both. I personally rediscovered isomorphism between systems or disciplines several years ago and called it a metaphorical bijection. I wish I read 2 books that I mentioned at the last resources, on the last resources slide. And so, therefore, the new disciplines can be created in such a manner. As an example, I repeat here software narratology that covers all types of narrative in software construction and post-construction phases. Just another notion from system theory, the so-called complementarity of artifacts here. One of the general system properties is the notion of this complementarity, where 2 or more independent things improve our diagnostics abilities or problem-solving abilities. In software diagnostics, we have memory dump versus software traces, where memory dumps are static, software traces are dynamic. As noted previously, network traces are considered the same as software traces in principle. And so, in addition to software artifact complementarity, there is also a complementarity of reports, such as when several observers of software diagnosticians or tech support engineers or software developers see different patterns in the same log. The obvious solution is to use checklists here, pattern checklists. So another notion is complementarity of analysis. Here we mean malware-victimware dichotomy. For example, you can find the reference to victimware presentation on the reference slide later. So far we have seen all different types of complementarity, artifact, reports, and analysis. Another notion in system theory is decomposition of behavior. So here by decomposition of software behavior, we mean using different tools to trace different aspects of software behavior simultaneously in order to reduce diagnostics artifact complexity. So all different types of artifacts, traces. So finally, what we have is the notion of holistic approach. Systemic approaches are often associated with holism, where the sum, roughly the sum is more than the sum, so the whole is more than the sum of its parts. So here, even if we use different tools for tracing different aspects, the so-called, as we noted previously, decomposition of software behavior, we should also strive to record all possible events and use artifact analysis tools to do filtering for us later. In such cases, we minimize an impact of not recording important events, especially for first fault cases. Now we come to the so-called diagnostics complexity. So here another notion that arises in system science is the so-called complexity. And the example we provide here is for memory dump analysis. For memory dumps, the complexity or diagnostics difficulty we think depends on structural complexity, the number of components and their relationships, the number of diagnostics tools and their commands, and the number of patterns in a catalog. The more patterns we have, the better. The more tools and commands we have, the easier is diagnosis. For example, GDB has less commands, so to make the diagnostics effective, as WinDBG from debugging tools for Windows, we have to use additional tools such as VMMap and diagnostic reports in addition to core dumps. And finally, a few words about first fault diagnosis. Software diagnostics is also a first fault software problem tool because all patterns are first fault. Most patterns, I would say. Of course, it depends on whether artifacts are collected on the first fault occurrence or not. I put here a link to a book by Dan Squire that first pointed to me such an important distinction between first fault and second fault tools. Just a bit of ad. Here, Software Diagnostics Services plans to release a workbench tool to help with day-to-day software tasks, software diagnostics tasks and activities. So for details, please visit the link later on. It's called Software Diagnostics Workbench. And finally, a joke. I rarely make jokes during presentations. However, today we have an example of my abnormal behavior. So you see a systems joke at the end. So basically I just reversed W and make Mhole in a hole. So provide some parallels with intelligence analysis via signals intelligence and human intelligence. So a new approach to software diagnostics via moles or memory holes. Hope you find this funny. So in further reading, I put two book titles that are very helpful in studying systems thinking and corresponding science. The one is very famous, is an introduction to general systems thinking, and the other is textbook, but the first part of it is very useful. And I also included links to relevant presentations and books from Software Diagnostics Institute and Software Diagnostics Services. So we also plan next webinar. It would be about abductive reasoning in software diagnostics somewhere in December. That has to be announced, the exact date. It's about abductive reasoning. where we infer explanations from patterns. So this webinar repeat will be focused on abductive reasoning, where consequences are used to infer possible and most likely explanations that guide further troubleshooting and debugging efforts. And we also cover the difference between abduction, deduction, and induction. So it's a bit confusing. That's it. So I'm also very interested in how to improve this introduction. So please send your comments and suggestions. If I can't answer your questions now, I then post it on Software Diagnostics Services website later this week. So I also plan to put the recording of this webinar later on, after I check it, and publish a transcript. And I also put a PDF file later today, so you all can download and use check links, various links. So again, thank you for attending this webinar. And I also plan version 2 early next year, especially after I do abductive reasoning webinar and check also pattern-driven software diagnostics, the first version of the previous webinar, in light of systemic software diagnostics webinar, abductive reasoning, and other topics. So, okay, if you don't have any questions, you can always send them later using the contact form. So thank you all for attending again, and see you next time. Bye-bye.